Hello, Assalamualaikum warahmatullahi wabarakatuh, and greetings to all of our lecturers. Thank you for watching this video, and today we will be presenting our integrated design project for Group 3-10, and this project consists of courses from Separation Process 2, Reaction Engineering 1, and Process Modeling and Simulation. So, without further ado, let's meet our team. So my name is Jabir Meftah, and my other teammates are Ramana, Ganesraoo, Siti, Aisyah, and Sharifah, Rabiah. So let's check on our table of content for today. So our content will be split into 4. The first one will be covering reaction engineering, second one will be covering process modeling and simulation, third one will be separation process 2, and of course last one is conclusion. So we'll be covering the introduction, the objective, and the overview of each courses, and of course the overall conclusion will be summarizing everything. So that's it for my part, so pass on to the next one.
Assalamualaikum and hi, my name is Siti Aisyah and I will be presenting on the reaction engineering part. From the introduction, biomass is predicted to be the main energy source in the future. Therefore, an optimum reaction system for pyrolyzed biomass gasification is to be designed under optimal operating conditions. There are 4 main objectives for this case study, which are as shown in the slide. For this reaction, 2 packed bed reactors are chosen as the gasifier. The first PBR will undergo oxidation reaction, which are water-gas shift reaction and partial combustion, whereas the second PBR will undergo reduction reaction, which are methanation and methane steam reforming. There are several advantages of using a continuous packed bed reactor, which is why it is chosen for this reaction. Both oxidation and reduction reaction occur in the 2 PBR at the same temperature and pressure, which are 800 degrees Celsius and 1 atm respectively. However, the type of catalyst used is different, which is as shown in the slide. As for the sizing of reactor, from the calculation, it is found out that volume of PFR1 and PFR2 needs to be at least 12,524.09 m3 and 5,737.22 m3 respectively in order for the reaction to occur accordingly.
Hi, I'm Ramana and I'll be your guide throughout chapter 3. Let's go. Process modeling and simulation. Wow, it's really a mouthful to say. But what is it really and why do we need it? I'll tell you in a few minutes if you bear with me, so let's go to the next slide. Process modeling and simulation is very important in a process design. It can forecast the outcomes and data that may emerge from actual built infrastructure. Also, the simulation would be used to stimulate reactor sizing, conversion, and stream conditions. Here you can see our very first mathematical model that we have designed for this process. Since we will be using 2 PBR reactors, which means that we have 2 PFRs, the first one is shown as in the slide. And so the assumptions we have clearly stated, where we have perfect mixing, first order reaction for both reactions, and overall heat transfer coefficient, the kinetic energy and potential energy all equals to 0. While the objectives would be to develop a model that enables the determination and species concentration profile, and also to develop a model that enables the determination of the temperature inside the packed bed reactor. So obviously this would be the second reactor because we only have 2. And so the assumptions for this would be the same. Perfectly mixed first order reaction, Cp, Vp, overall heat transfer coefficient equals to constant, and the kinetic energy, potential energy, and work equals to 0. While the objectives would be to develop model that enables the determination of species concentration profile, to develop model that enables the determination of the temperature inside the packed bed reactor. And so now we have come to the most awaiting moment, the simulation diagram. Let's go. So this is our final simulation results. We took a long time trying to figure out how to produce our simulation. And as you can see, we have three streamlines, which means we have three streams, and then we have the PFR1, PFR2, and the QR2. So by this simulation, we will be able to observe and analyze the major factors that will affect our reactor performance in this process based on all of the data and results. We also get the opportunity to provide an appropriate and relevant solution for the devices based on specifications.
Hi, I'm Rabiah, and today I'll be talking about Chapter 4, which is about separation process 2. So first of all, for Chapter 4, we are required to design a downstream separation from the system for the removal of contaminants from syngas. So raw syngas contains minor but significant quantities of undesirable impurities, collectively known as syngas contaminants. Syngas contaminants are composed of tars, nitrogen-based compounds such as ammonia, sulfur-based compounds such as hydrogen sulfide, hydrogen halides, and trace metals. So raw syngas cleanup is an essential step prior to syngas utilization in downstream applications. So as you can see, the picture shows the overall block flow diagram for our separation process unit. As you can see, we have two absorption units and one membrane unit. The first absorption unit is used to remove hydrogen sulfide and a bit of carbon dioxide from the syngas. The material used in absorption unit is both polyethylene glycol and copper sulfate. The reason behind this is because polyethylene glycol provides an efficient outcome in the removal of low concentration of hydrogen sulfide. Besides that, the removal of nitrogen-containing contaminants is normally achieved through wet scrubbing. And its true removal efficiency varies widely from 50% at 500 ppmv to greater than 95% at 200 ppmv, which is quite high. The material used for the absorption unit, the material used for the membrane is polyethylene oxide. So PEO is chosen as it has high selectivity towards CO2. In PEO containing copolymer membranes, the role of polar PEO sequences is mainly to selectively interact with polar gases such as CO2 in the feed mixture to enhance the selectivity towards the polar gases. Let's now talk about the efficiency, safety, maintenance, and cost of the separation units. First of all, regarding the efficiency, by using MDEA as a solvent for the absorption unit for the removal of contaminants from syngas, in this case specifically sulfur, the removal efficiency is 98 to 99% and it has a low capital cost. Next, regarding the cost of membrane separation unit, it is usually a challenge to keep the specific membrane cost figure low by achieving a less frequent membrane replacement. Usually, the total operating cost will be $15,314 USD to $13,629 USD with a membrane replacement cost, or better known as MRCs, of assumed $3,000 USD to $6,000 USD. This is because MRCs in industrial application are generally in the range of 10% to 20% of the total investment cost of a plant. Now, let's talk about the safety of both separation units, which is membrane separation unit and also the absorption unit. So the errors that could occur are corrosion, design fault, fire and explosion, human error, impact, impurities, maintenance faults, and so much more. This is why it is important to have backup plans such as an emergency response, a planned layout for people to escape if there is an emergency, a PPE, a secondary containment, and also a spill treatment in case anything happens. Now, I will be talking about the challenges faced in selecting the separation process unit along with its proposed solutions and strategy to maximize the production of purified product gases. So currently, the major limitations of adsorbents include the corrosiveness when mineral acids such as H2SO4 are used and their low removal efficiency are noticed. As there are very limited systematic studies using acid washing, future research activities could be carried out in this area to systematically evaluate mineral and organic acids and ultimately improve on the removal efficiency. Besides that, the gas cleanup of sulfur contaminants in syngas is also another challenge that we can observe when selecting the separation process unit. The main drawbacks of full gas cleanup strategies for sulfur removal are syngas cooling, which then increases the capital cost due to refrigeration and solvent generation requirements. Another challenge for the absorption unit is regarding the selection of solvent. Benefits of oil-based scrubbing technologies are the possibility to operate at higher temperatures, thereby improving the overall process efficiency. However, the major drawbacks of using oil-based scrubbing systems for tar removal is that it results in an increase in the cost of oil-based absorbents, which then results in an overall increase in cost. For this reason, this approach is currently economically attractive only in large-scale installations, not in small-scale installations. As for the strategy to maximize the production of purified product gases, our strategy is to add another separation unit for the removal of CO2 to increase the selectivity of the H2. This is because we can increase the selectivity of the H2 by using the membrane to filtrate the undesired product so it will not form, or the concentration of the side product will be minimal. The CO production can be significantly reduced due to the incipient removal of hydrogen through the membrane. The emitted hydrogen can be separated from CO by means of a hydrogen selective diaphragm inside the membrane reactor, leading at the outlet of the membrane reactor to two separate streams of H2 and CO. Thank you.
So that's it for our video today. I hope you all enjoyed. So we'll be having a quick summary and overview of what we've been through. The first one is introduction, second one is reaction engineering one, and then the third one is process modeling and simulation, and then we have separation process 2, and of course the conclusion. So before we end this presentation, we would like to leave you all with a quote. Projects we have completed demonstrate what we know. Future projects decide what we will learn, by Dr. Mohsin Tiwana. Thank you very much. I hope you all enjoyed our presentation. We express our greatest gratitude to all of our lecturers who have guided us throughout this whole integrated design project covering 3 courses. Thank you very much and goodbye.